Hey everyone, in this video we will be talking about Taylor series. So the first question might be, what are Taylor series? So we've actually already seen a couple of these. So e to the x is the sum of x to the k over k factorial. So we've already seen this representation. We just didn't know it's specifically a Taylor series. And the same with like sine of x being 1 minus x cubed over 3 factorial plus x to the fifth over 5 factorial and so on. Essentially the odd terms from the e to the x power series, but alternating in sign. So the real issue here is that power series are useful. We like power series. They allow us to integrate things like sine of x squared and have a nice form, whereas we wouldn't be able to do that with normal integration, but it's nice using integration term by term of our infinite series. But we also have an issue of how do we find these in general, right? So for instance, not all functions have power series. The absolute value centered at 0 is an example. Basically, you can see that because if it did have a power series, its derivative would also be a power series. And you can do that term by term, but the issue is this doesn't have a derivative at 0, so it couldn't have had a power series to begin with. And then the other issue is convergence, right? Even if we do have a power series representation, they don't always converge for many values of x. You may have a very small interval of convergence. And these guys up here, these examples, both converge everywhere, which is super nice. So how do we actually come up with these things? Okay, so the idea here is we are going to build this one step at a time. So we're going to start with p0. So here I'm going to let f of x be e to the x. p0 is just going to be a constant term. And so we're going to start with like the worst approximation. What constant will we use if we wanted to center this at 0, say? So we center at 0. How would we best approximate our function e to the x? Well, you would just do e to the 0 because we want to match specifically at this point, right? We want to match that guy. And so this is just 1. And obviously it works at that point, and then anywhere else it becomes a pretty bad approximation really fast because e to the x is not constant at 1. So then the next thing you might want to do is see, okay, well, can I make sure that the slope works near my point, right? So I can look at like the tangent line to approximate, for instance. And so what you want to do is we find p1 of x, which is going to be now a linear function, a line, that still agrees on the first point. And then we want some coefficient in front of x such that p1 prime of 0, our center, is the same as f prime of 0. But f prime of 0, of course, well, f prime of x, any derivative of x here is going to be e to the x still, right? And so if we plug in 0, we're going to get 1. And so, well, what is p1 prime here? Well, that's just going to be a in this case, right? Because the constant goes to 0. And so we want a to be 1. And so we now get what's called the first Taylor polynomial, right? Because we're building an infinite polynomial, which is our series. And this is now going to be 1 plus x. But then that's still, right, it's not like a line. It is going to get increasingly off toward infinity as we move to the right. And so the next thing you might think is, okay, we got the right value of y. We then got the right slope. Then the next thing is to match this concavity, right, and start to get the curve right. And so that's about the second derivative. And so now we're going to add another piece to our polynomial, right? We're going to build off of this. And then we go to bx squared such that our second derivatives match. So we want p2 double prime of 0 to be f double prime of 0, which again is 1. And then what's the second derivative of this? Well, anything before our x squared term is going to go to 0. And then this guy will become 2b. And thus b is going to be 1/2. So now we know that p2 of x is 1 plus x squared over 2. And then you can keep doing this process. And of course, once we get past concavity, it's not quite so clear graphically what we're matching, but the idea is that we just keep adding terms of our polynomial, and we get better and better approximations. And so maybe I'll do one more term here. So we'll do plus cx cubed. And so again, you want the third derivative at 0 to be equal to 1. And then what's our third derivative here? So again, all of the things before go to 0. And then when you take the derivatives, you get, 3cx squared, then you get 6cx, and then you get 6c. And so we want 6c equal to 1, or c to be 1/6. But also you might notice like what's happening with this power rule, we get 2 times 1. We get 3 times 2 times 1. The next one will be 4 times 3 times 2 times 1. This is really 1 over 3 factorial that we're seeing here. So then we can continue this process and get our general nth degree, what's called the Taylor polynomial, for specifically e to the x here, centered at 0. And so here our Pn of x is, well, we just do exactly what we did, get our 2 factorial, we get x cubed over 3 factorial, and then we cut it off eventually at the nth degree and get x to the n over n factorial. But of course this video is called Taylor series, right? And so there we actually want the infinite polynomial. We don't want to stop. We don't ever want to truncate it. And so you would go n equals 0 to infinity of your Pn of x, right? These are basically the partial sums. And so if you don't stop anywhere, you just get this series for e to the x. Okay, so here is the general form. So if f has all of its derivatives existing at our base point x0, then it has a Taylor series, and it is exactly of this form here, where our ak, our coefficient out front, is the kth derivative, and you plug in your base point, and then you divide by k factorial. And just for that example with e to the x, right, our f to the k of 0 was always 1, and so this is why we got a to the k is 1 over k factorial. And so we got x minus 0 to the k, or x to the k over k factorial. So now let's look at one example where we're not centered at 0. So we're going to check out the natural log of x, which of course we don't want to plug in 0 because we can't. And so instead here we're going to center it at x equals 1. So our first process is just to find all of the derivatives here, okay, and start to at least see a pattern. So f prime is 1 over x, f double prime is negative 1 over x squared, f triple prime, right, you have like a negative 2 down there, so we switch signs again, and you get 2 over x cubed, and we'll maybe do one more, and we get negative 6 over x to the 4th. And so in general, if you want the kth derivative of x, what do we see happening here? Well, we have an alternating sign, so it's negative 1 to the something, and on the even ones it's positive, or sorry, on the even ones it's negative, and so we want like a k plus 1 there. And then up top here, we seem to have the factorial going on, but it's 1 below our thing, so this is like k minus 1 factorial over x to the k. And so then we could just plug in our center, right? And that just gives us 1 in the denominator, so we get negative 1 to the k plus 1 times k minus 1 factorial. And so then ak is going to be that guy over k factorial. But then we get a ton of cancellation here, right? Because the k minus 1 factorial is gone, cancels with the k factorial, and leaves just k on the bottom. And so this means that our series is going to be from k equals, well here, 1 to infinity, because we don't want to divide by 0, of negative 1 to the k plus 1. And remember that we're centered at 1 here, so we want x minus 1 to the k all over k. And if you can't see the pattern there necessarily, you can just go up here and start writing out terms, right? So you could alternatively look up here and see this is 1, the next one gives you negative 1, next one gives you 2, then you get negative 6, and so you start to see the pattern here as negative 1 to the k plus 1 times k minus 1 factorial kind of thing going on. And so for your exercise, I want you to find the Taylor series for cosine of x centered at x equals 0. And I recommend that you actually graph out a few of these terms, maybe up to like the 10th degree or something, and see how close it actually starts approximating your curve. It's pretty interesting. All right, thank you for watching.